Okay, welcome to the afternoon session. My name is Torsten. I'm going to give you a brief introduction to Neural Radiance Fields, or NeRFs for short. If you ever search for those things on the internet, don't type NeRF. We'll end up with a lot of toy guns, but not the thing that you're interested in. If you have any questions at any point in time, feel free to stop me and we'll talk about it directly, rather than waiting until the end. Good. So my background is in computer vision, and I'm interested in building 3D models or 3D reconstructions of scenes from images. And that's precisely what NeRFs are doing to some degree. The input is a set of images with known intrinsic calibrations and camera poses, and we would like to have a faithful reconstruction of the scene. And traditionally, these things have been done using explicit scene representation. So you have, when you reconstructed a scene, you try to build a point cloud or some 3D mesh. This is what, for example, multi-view stereo methods give you. They work well. The problem is that they are quite memory intensive, and you make the assumption that you have Lambertian surfaces, meaning the color of each part of the scene doesn't change depending on from which direction you look at. An alternative to explicit scene representations are implicit scene representations. The most well-known is probably the sign distance function. So if you have a simple shape, for example, such as a circle, the sign distance on the surface is 0, and as you move away from the surface, the sign distance to that surface increases. If you move into the surface, the sign distance decreases, or you get negative values. And those things have been used for 3D reconstruction for some time. We did, like a few years ago, live reconstruction using implicit implicit scene representation, sign distance function on a mobile device, where you would actually use a fisheye camera to compute depth maps, and these would then be integrated into a sign distance function. And once you have the sign distance function, you can extract a mesh, which is rendered on the large part of the screen by essentially finding the zero crossing of the sign distance function. The way that traditionally this is implemented is you voxelize a scene, so you compute a discrete subdivision of the scene, and in each voxel you store the corresponding sign distance function. And as I said, you get the geometry or 3D mesh by finding the zero crossing of the sign distance function, which by definition is exactly the surface of the scene. The issue here is, again, because you need to store a voxel grid, this becomes quite memory intensive. And again, you make the assumption that you have Lambertian surfaces. And this is where essentially NeRFs come in. Here, what you see on the left is actually not a real image, but a rendering from a neural radiance field. And on the right, you see the geometry that the NeRF learns as part of the training process. As you can see, you're able to actually faithfully reconstruct the scene in high detail, both in terms of color and in terms of geometry. So you can get high quality geometry out of these things. At the same time, you can model complex illumination, complex like interactions between light and the scene, such as like reflections, refractions, and so on and so on. Again, these are not real images, these are renderings. So you're actually able to handle non-Lambertian surfaces quite well. And at the same time, these neural radiance fields can be rather compact. So what you see here is a 3D reconstruction system that takes color and depth images as input and then trains on the fly a neural radiance field to represent the scene. And I think the scene representation that they use is about 1 megabyte for a rule. So you end up with something very, very compact. Good, so I hope that motivated you that NeRFs are something useful. Let's look into what they are and how we train them. And they build up on something that was invented in the 80s. It's slightly younger than me, the paper, and it's volume rendering. So the idea is that you have some representation of the volume, If you have an image that you want to render, you want to compute a color for this pixel, you essentially shoot a ray into the scene. You sample 3 points along the scene, and at each sample point you evaluate your volume, you get a color and some volume density. And you essentially accumulate all these samples, like the colors, combine them in linear fashion, and that gives you the final color for that pixel. Back then, I think someone said in 10 years all rendering will be volumetric rendering. We weren't there in the 90s. We might get there now with neural radiance fields. So how do we actually get the color? So we have this array that we shoot for each pixel. We have samples. For each sample, we have a color which is RGB, and a volume density, which essentially says, is this part of the space occupied or close to some surface or not? If it's not occupied, you get basically 0. Otherwise, you get a large value. The value doesn't have to be between 0 and 1, but it could have like larger values. So, and then the final color, as I said, is a linear combination of these individual colors. More precisely, the way that you compute it is this. There is a visibility term, and that's used to weight the color. And this visibility term consists of 2 things. Like this thing looks just at the current sample. It uses the distance between this sample and the next sample, assuming that volume density and color remain the same here. And essentially what happens here is that if you are in an occupied part of the space, meaning sigma I is a large value, then this part becomes small, and you have something that's close to 1, so you give a high weight to this. If you're in a non-occupied part of the space, then the sigma value is close to 0, meaning the exponential is close to 1. This cancels out, and you get very, very little weight. The TI term essentially looks at all previous samples by essentially looking at like the individual distances and weighting them by the corresponding volume densities. If you are here and if all of these previous samples were an empty space, then this part will essentially be 0. So you get a weight of 1. If one of these previous samples was occupied, then you will get some larger term, meaning the exponential becomes small and you give less weight to that color. Let's try to illustrate this a bit. We will call this individual term beta I here. And let's look at like the distribution of volume densities. Let's assume this is our volume density, the ground truth. Then at the first sample, we haven't encountered like anything before. So this is 0, meaning T1 is 1. Since we are far away from like high volume density, this part is 0, so this part becomes 0 as well. As we go to approach the volume density, the TI term stays close to 1 or 1 because we haven't seen any reasonable volume density before. As we hit the peak, the TI term is still 1 because none of this was actually, none of the samples before had any density. But the beta term now also becomes large because this part becomes large, so this part becomes small, so this is close to 1. We get the next sample, which is again in a region that has no volume density, so the beta part is 0, but the TI part is also 0 because you are close to 0 because you encountered one sample with a high volume density. So meaning this is a large term, this is a small term. And so on and so on. So hopefully that gives you an idea what this volume rendering does is essentially takes into account individual color samples and weights them based on some sort of visibility. Is this part visible, or should it be visible or not? Good. So what we assume is that we have some volume function that gives us these density values and the color values. What you should notice that this whole function is very simple. It's fully differentiable. And this is where NeRFs come in. NeRFs are essentially nothing else than saying, look, I'm going, rather than assuming that I have captured these volume densities and colors with some special equipment or so, or they're given, I'm actually trying to train them from images. So I want to learn a volumetric representation. And what you essentially do is you train a neural network that takes 5 parameters as input. These 5 parameters are the position, like 3 parameters of these 5 are the position of the 3D point, and then you get 2 angles that describe from which direction are you looking at this 3D point, so that you can essentially model view-dependent effects where you continue looking at the same 3D point from different viewpoints, and then the color and the volume density, or the color that's outputted by the network, can change according to the change in viewpoint. So you end up with a scene representation that's continuous compared to the discrete representations that you had for voxel volumes. So for a NeRF, when you would render an image, you essentially do volume rendering, you shoot a ray through the pixel, you sample 3D points along the ray. That gives you, together with the direction of this ray in 3D space, gives you the input to the neural network, and the neural network gives you color and density for each of these samples. So you end up with a color for each pixel computed using volume rendering. So how do you train the NeRF? You assume that you have a set of images with known poses. During training, you can generate rays by shooting pixels through the images. You compute the color. You have the color for that pixel that is actually in the image. You have the color that is predicted by the Neural Radiance Field. And what you want to do during training is you want to make sure that the color that's predicted is as similar as possible to the color in the actual image. So, very simple training objective. In order to make things work, you need to do a few tricks. So first one is be a bit careful on how you generate the samples. Yes?
What about density and subjective function?
We don't have any ground truths for the density typically. From images, you don't have an idea of where exactly along the ray the volume is. But that's something, where along the ray the surface is. So that's something that the neural network need to figure out. It's a free parameter, so to speak, that you need to estimate. If you had, say, depth images, then you could add a supervision term where it's saying, I would like to my volume density to be high, close to the depth values that I observe, and 0 otherwise. If you sample along the ray, then you typically assume that you know roughly how far away the camera is from the scene. So you can define a near plane and a far plane, which says I'm only interested in sampling values in between. And you would subdivide the distance between the near and far plane into equal intervals. And then during training, rather than sample at fixed positions, you would, for each interval, you would randomly select some point in this interval. The reason why you do this is if you would sample at fixed positions, you only train the network at fixed positions. If you uniformly sample during training, you essentially cover the space more continuously. So here you hope that you would hit something that's close to the surface, but you're not really guaranteed to draw a lot of samples actually at the surface. But if you evaluate the network at these sample points, you actually get an idea of how the volume density is distributed, because for each sample point you get a density estimate. So you can fit some sort of curve. and then can do a second sampling step, where you would draw your samples according to the volume density that you have observed before. So the idea of this fine network is that rather than trying to uniformly guess where the density is, you get a reasonable guess, hopefully from this core stage, and then you do educated sampling. And that typically improves performance quite a lot. And if you do rendering, you would typically take the samples that you get from the coarse network and the fine network to compute the final color. So at least in the original NeRF implementation, you actually would train two NeRFs, one based on coarse sampling and one based on fine sampling. And you would simply add a second cost term where you would compare the ground truth color with one, the color predicted by the fine network, and the color predicted by the coarse network. That's not all that you need to do in order to train those things properly. One important detail is that you don't actually have one single neural network, but you actually have two. The first one takes only the position of the 3D point as input and outputs some feature vector and a volume density. And the idea is that the density of the space, where surfaces are, should not depend on from which direction you're looking at, but that's something that's fixed in the scene. And you would then take essentially the volume density, this feature vector, and the viewing direction of the ray as input to a second network that then predicts the color. If you do all these tricks and you try to train a NeRF, you'll get something that looks something like this, which is not very appealing, right? So what has gone wrong here? It turns out that neural networks are not really good at predicting fine details if you give them just coordinates. But there's a simple trick where you, rather than giving the original XYZ coordinate, you lift them, you encode them into some higher dimensional space, and then feed them into the neural network. Same with the direction of the array. And one simple way of doing this input encoding is to essentially look at each coordinate and compute various sine and cosine terms. Some sort of frequency encoding, similar to what people are doing for transformers, for example. And it has been shown that this helps networks to recover fine details that you would otherwise lose if you just give XYZ. So if you do this positional encoding, then this is a difference between just taking XYZ and to the viewing direction of the ray versus doing an input encoding for each of the 5 values without changing anything else. So it makes a significant difference. Let's look at some results. This is on synthetic scenes. On the left, you see some previous method. On the right, you see the output of the NeRF. This is essentially the nearest training view, a training view that's closest to the view from which is currently rendered. And as you can see, you're able to recover fine details while also taking into account view-dependent effects such as reflections on this watery surface. So again, you see that you're able to reproduce fine details such as the individual links between the parts of the instrument. So this is synthetic data. This is on real scenes. It's not like complex scenes, complex motion. But you can see that you're able to faithfully reproduce fine details. Any questions so far? Yeah?
What exactly represents the density
So if you would have solid objects, and ideally you have 0 everywhere where there's free space, and then some high value on the surface and inside the object. But the thing doesn't really have like an intuitive meaning, at least in my experience. It is essentially, is there something, or are we close to something or not? It actually causes problems, and we'll see this later on if you want to extract the surface, because it's not uniquely defined. We'll get to that later. Any other questions? So we get wonderfully nice images. Everything is good, right? Research done. We're going to sell this to some company or whatever. There's one disadvantage though, which is NeRFs are, at least in the original formulation, horribly slow. Because for each point, you need to query and evaluate this neural network. And depending on how complex your neural network is, that can give you like a few days for training such a simple scene. And rendering an image can take seconds to minutes. So how do we make this faster? One question to ask is, do we actually really need a neural network, or can we do things in a much more simpler way? And it turns out that you actually don't necessarily need a neural network. So there's this paper called Plenoxels, which showed I can actually get competitive results without actually any deep learning, just using differentiable volume rendering and a slightly different representation of colors. So the idea is, rather than training a single neural network that represents a scene, you go back to like a more explicit representation where you subdivide the scene into voxels. And at the corners of each voxel, you store essentially a volume density value and like a spherical harmonics coefficient that you can combine into a color. If you sample, like if you want to evaluate some 3-point along the ray that falls into a voxel, you compute the corresponding spherical harmonics coefficient by a trilinear interpolation of the coefficients that you store at the corners. Take like where the interpolation is done based on the spatial position of that point in the voxel. So that gives you some color, that gives you volume density. You can do volumetric rendering, and you can optimize essentially the same reconstruction loss that we had before. Essentially the idea is that rather than optimizing the weights of a neural network, you optimize the weights of these spherical harmonics. And the promise there is that because you have like a much shallower representation, rather than having like a deep neural network, you have like a few, like I think 32 parameters or so that you optimize per vertex. This is something that's much faster to evaluate, and thus much faster to render and train. One issue is if you take this original, like this formulation, you will end up with renderings like this, where you have a lot of noise. And what happens is that you actually have so many degrees of freedom that you can overfit to the individual colors without enforcing any smoothness. So what this paper then actually proposes, then rather than just looking at the reconstruction loss, you also have some regularization term that says, I would like to, if possible, have a smooth transition between voxels. And if you add regularization, you get much more meaningful results. This is not perfect, so here there should be a lot of ferns that are not reconstructed. But the advantage of this thing is that it's significantly faster than training a neural network. So here on the left you see the current state of a neural network, and while this is still trying to figure out what's happening, the Plenoxel has already been trained. And then everything else refines quality, but even after a few minutes, you actually already have a result. Here are some results on simple real-world scenes, where again, you can see that you don't necessarily need to learn like a neural network that represents a radiance field, but you can directly parameterize this in a much easier way, which I think is a very nice result showing that you don't necessarily always need deep learning. Here are results for a bit more complex scene. You can see that things are much more blurry. That comes from the fact that you have maybe a couple of hundred images in the scene, so you observe each scene part in a few images from potentially a few meters away, so you don't have that much detail to recover. But still, you can see that this non-deep representation is able to model view-dependent effects quite well. So what's happening here? Why does this work? It essentially works because you have a dense enough grid of the voxel grid of the scene. And you actually need this because you're going to, if you compute volume densities, you're doing trilinear interpolation, meaning you make the assumption that within the voxel, you have like essentially a linear relationship in how your volume density changes. That means you actually have to have quite detailed subdivision of the scene for this linear approximation to hold, which in turn means what we have actually done is we have made training and rendering much faster at the cost of actually higher memory. Because we have this detailed voxel grid. For each voxel, we need to store multiple features, or like a 30-dimensional vector, and that quickly, the memory of this quickly grows. How can we try to reduce this so that we both get fast rendering and training times at a reasonable increase in memory? And the idea is that you can take a step back, and this Plenoxel essentially had trainable features associated with each vertex of your neural network. And rather than just computing a color from this directly, you could compute the trilinear interpolation of your features to get a feature for a point on the ray, add some additional information such as the viewing direction of the ray, and then feed this into a small neural network, where the idea is that rather than having to encode everything explicitly in the features and having a fine enough subdivision that like linear interpolation makes sense, you have this neural network that can model nonlinearities. That hopefully then means that you can have like a coarser subdivision combined with a small neural network, and you would jointly train these features and the neural networks. So here's some example. On the left, you see the output of a standard NeRF, where the neural network has about 440,000 parameters, and training to this quality takes around 14 minutes. And then the next one, you see a multi-resolution grid approach, which is based on voxelizing a scene. You have like a very small neural network, which only has 10,000 parameters, but you also have 16 million parameters that come from the features stored in at the corners of the voxels. So you have increased memory, but you have decreased training time to like 1.5 minutes, because in each iteration you only need to update like a few parameters of the neural network and a few features. You never need to look at all 16 millions of them. Still, you see a decrease in quality, which naturally leads to the question is, can we actually improve quality while also reducing memory requirements? And turns out, yes, you can do this by doing a multi-resolution hash encoding of your features. So the idea is pretty simple. You have multiple grids that subdivide the scene. For each corner, you hash the point position into like a value in a hash map, and you store like a short feature vector in that position. And you do this at multiple resolutions. You have like multiple grids to get the color value for the point that you want to evaluate. You take the hashed feature, features that you get from the hash map, and you do linear interpolation within the voxel. You concatenate all of this. You potentially add some extra information such as viewing direction, and you run this through a neural network. So the difference here to the previous multi-resolution approach is that you reduce the number of parameters by essentially hashing 3D points into fixed size hash maps. And you essentially would use the same hash table size for each resolution, which at coarse resolution actually gives you an injective mapping where each point is mapped to a unique cell in the entry in the hash map, so you don't have any collisions. But you will get collisions when you start having finer subdivisions. These are actually not handled, but everything that you can have multiple points mapping to the same entry, and you never really try to resolve this, but rather during training, what happens is that multiple individual points get mapped to the same entry. You get multiple gradients for updating the feature of that entry coming from different 3D points. And the idea is that in many cases, there's only a few gradients that are large that will actually help you improve the network. The rest is small because you're sampling regions of the space that are empty. So the idea is, our intuition is that the network will actually handle collisions by itself by essentially you would first take care of large gradients because they give you a large, they much more contribute to the update of the feature. If you do this, so here's an example of this approach using a hash table. You go from 60 million parameters to 500,000. You keep training time roughly the same, but significantly increase quality. And if you combine this with a highly efficient implementation of neural networks, then you get something where you can train neural networks like NeRFs in a few milliseconds, few seconds. You might have heard about it, so-called instance NGP, instant neural graphics primitives. It's a very nice software package from NVIDIA that they released. So let's have a quick look at this. So what you see here is the Neural Radiance Field getting trained. And you directly see the output of this. You see that here you can see the training loss, which is decreasing, and as the training loss is decreasing, the quality of the renderings increases. And after a couple of seconds, you already have something that's meaningful. After a bit more time, you start seeing more and more details. You can also visualize the cameras from which are used to, from which the images were taken. So this is a video sequence. It's just essentially me running around the statue.
How did you
you can see that the positions of the cameras that are extracted from, or images that are extracted from the video. I think after a few seconds you can you can see that it kind of is modeling some shadow that's a bit view dependent here. There's also a bit of a subtle effect. You will see this after a few seconds of training, that here you actually get some details, whereas if you're looking from the other direction, everything gets like saturated because you had direct sunlight. So you actually see that it's able to model view-dependent effects. As part of the neural network, and this is a bit hard to do if you don't see it, you can actually not only estimate like the entries of your neural radiance field, but you can also update the intrinsic and extrinsic parameters of your cameras. So you see that it slightly starts shifting the camera poses, and it should add you a bit of detail to the neural network, to the representation, because it's essentially able to optimize the camera pose so that you get crisper renderings. And typically, this works within a few minutes. You get something reasonable, at least for smaller scenes.
So it actually starts with the information, like the time-based information. That, for example, when you go from one angle, the sun is up, and then you go from the other angle, and the sun, for example, it's obscured by the cloud.
Yeah.
You go from the other direction, the sea is dark, and from the other.
Yes, so because it has this degree of freedom, which is you can model like colors depending on from which direction you're looking at. That does not help you with moving people, right? Because that you can't just model as an effect. We're actually going to look into like occluders and so on the next slides. Is there any question about? Yeah. The hash table maps from 3D point positions to some feature, like a two-dimensional feature typically, that encodes some information about color density for that point. And you do this at multiple resolutions. For a query point, you get the corresponding features by linear interpolation based on the position of the point in the voxel. And then you concatenate the different interpolated features, feed them in the network, and ask the network to give you color and density. Similar to how we encoded the position with like those lines. Yes, it's essentially a learned encoding if you want to do this. Yes, yeah.
Could you expand on what inputs and outputs here are? Because I guess this training of feature vectors should be like color associated with viewing, or I'm not quite.
So the input to the whole training process is still images with known poses and intrinsics. And essentially what, in this spherical harmonics example, you essentially said, I know that I need to represent colors. I represent colors in like as coefficients of a spherical harmonic function. And
doesn't it also depend on the viewing angle? So here you have to encode from perspective.
Yes. So you would do, you would evaluate the color based on position and viewing direction. And the same happens here, only that you tell, I don't know how to model, I don't want to define how to model it, but I would like the training process to figure this out. So you just say, it's a couple of numbers. They are not necessarily like humanly interpretable, that the first number is color and the last number is whatever. but you just get like a vector representation that you can throw into a neural network and something meaningful comes out. The y would be the input, which is this concatenated feature vector, and theta would be the parameters of the network that you want to optimize. So you would optimize, you would get a color as output. You would compare the color that you get from the network to the color of the pixel. And then based on the difference in color, you update the parameters of the network and you update the input to the network. Whereas the input to the network depends on the features, so you actually update the features that are stored at the corners of the voxels. Just think of this as some vector in a high-dimensional space, and as part of the training process, you learn this neural network, and you learn to structure the space in a manner that makes sense to the network. Any other questions? Yep.
I'm wondering, it seems like the application of NeRFs is like storing of color network rendering.
Yep.
Is it possible to use it to store geometry information or at least that information?
So what you can do is, rather than accumulating color, you could essentially try to figure out, you look at the occupancy values that you get, and you try to figure out, based on the occupancies that I see, where do I think the depths, like the geometry should be, and that gives you a depth map. So this is the same neural network trained, but rather than showing colors, I'm trying to show depths. So darker colors, except black, mean something close, white colors mean something far. Admittedly, the way that they show depths here is not really easily to see. I will run a second framework later where I can see this. But yes, you get geometry out of this, or you can get geometry.
It makes sense getting the input from the color as we use the NeRF to represent.
Yes, so you can use, if you have depths, you could have additional loss functions that essentially says, I would like to have high volume density around the predicted, like the depths that I get from my depth camera. Yes. I mean, if the object is transparent, you don't get, and I'll have an example for this, you don't necessarily get depths where you would get like a meaningful surface, I think. You can probably reformulate this in a bit, but the problem is that if you have a translucent surface, there's nothing that forces a network to say, there's one jump in volume density around the, say, you have this bottle, there's nothing that forces the network to say, if I enter here, there's one jump in volume density, then I get to 0 inside, and there's one jump when I go out. But you could also just have some constant volume density within the whole thing. That makes it not fully opaque, but translucent enough that you can look through this. So there's nothing that forces the network to say, there's really just one peak here, one peak there, nothing in between. So that makes it hard to actually get that like proper depths for things that are translucent. You can model the effect because it's something viewer dependent, and the network has enough capacity to model this. But the geometry behind this is a bit murky. Yes. You can also hear, where was it? What is typically a bit better is ambient occlusion, which has a bit of a better, more humanly visible rendering. And you can see that it manages to learn the geometry of the scene quite well here. Okay, one thing that you typically have if you look at images that you download from the internet, or if you capture things over time, is you see illumination changes from day to night, cloudy days, sunny days, and there are some sort of transient objects, humans walking in front of this. And it turns out that you can model these effects and still train a nerve for the static part of the scene. The idea is that rather than just training a neural network that predicts density and one that predicts color, you actually have you're training something that's called appearance embedding, which is, again, think of it as a feature in a relatively low dimensional space that encodes what's the appearance of the image. And you have a transient embedding, which is, again, a vector in a relatively low dimensional space that says where in the image that are used for training are objects that are not part of the static scene. So you have, at training time, you predict the static part of the scene, and you predict color and density for transient objects. So it looks something like this. Your inputs are like the viewpoint. You have some appearance embedding that you learn, and based on this, you can render the static part of the scene. Then you have this transient embedding, and together with the viewpoint that allows you to predict colors for transient objects per image, not in the full scene. Then you can combine the static rendering and the transient rendering. You get a reconstruction for the image, and you can compare it against the training image. Obviously, you get something blurred for transient objects because you most likely observe them only in one image, but you're also predicting some uncertainty that helps the training process to say, okay, I don't believe that these regions are really worth optimizing, so I focus on the rest. What is cool if you learn these appearance vectors, so here you see the depths that the network predicts and the color, but what you can do with these appearance vectors, you can actually take a novel viewpoint, you can render the scene from different viewpoints with different appearance vectors, and that allows you to essentially switch illumination conditions. So this is scene rendered from the same viewpoint under different, or from a small trajectory while at the same time varying the appearance vector. So you get different appearances for the scene. Meaning you can essentially, based on having training data captured at different conditions, you can relight the scene in an implicit way by interpolating between vectors. So far we have looked at mostly small scenes. You can also scale the whole thing up by essentially representing the scene not through a single NeRF, but having multiple NeRFs that you train based on images in a certain radius. And then if you want to predict a new image, you get contributions from multiple NeRFs potentially. This is a paper by Waymo, released last year, which showed that they could actually take Google Street View imagery and essentially train neural networks that represent downtown San Francisco, not just small scenes. And since they have data captured at different conditions, they can again relight the scene and simulate appearance under different conditions. Any questions so far? Now we actually come to your question about the geometry of this. So what happens if we want to get geometry from neural radiance fields? One idea would be to say, I believe that a certain density value corresponds to my surface, so I extract geometry as a level set for this density function. And if you do this, you get something that looks like that gives you a rough idea of what you're looking at, some skulls, some cans in front of a background, some statue, some apples here, but they are noisy. And the reason is that there's this defining geometry as a level set of some density value is not like a well-defined way of getting geometry. So like think of it as this way. You have your ray, you have volume density that you have estimated, and that's essentially your surface. You would like to have like a peak here. Well, when the ray enters the surface, the volume density inside remains high, and then it drops once you leave. So you could model, like the network might it might learn this volume density representation, but it might learn this and learn to compensate for the lower density by adjusting the color. So think of it this way. Here you have 0 volume density. It doesn't matter which color you have. Here you have non-zero, but you might find like a right color value and you might not see a difference at all. So there's a priori no definition of, it's not clear what's the right volume density. And as part of this, actually, your density might be drawn out rather than peaked, like you would like to have when you're extracting geometry. So in general, the issue is that this volume density is not really a good measure of 3D model geometry or surface. Luckily, there's a relatively simple solution, which is to say, rather than doing volume density, I actually estimate a signed distance function. When doing volume rendering, I have a way to translate from signed distance to volume density so that I can do volumetric rendering. And this helps because from signed distance function, the geometry is well defined essentially as the 0 level set of the signed distance function. So once I've trained this model, I can run something like a marching cubes algorithm after I subdivide the scene into voxels. If you do this, you get significantly better geometry if you try to extract it from this. So here you see that there's 2 cans stacked off each other in front of 2. I think there's a milk bag and there's probably some chips bag. You get a highly detailed 3D model of the skull here. You get details in the statue here. You get the different fruits here. So the corresponding method is called vol-SDF, or volume rendering of neural implicit surfaces. This works quite well in small toy data sets where you have many views seeing the scene. It starts getting a bit murkier in more complex scenes, where more complex is defined as I observe each part of the scene in only a few cameras. So here, this is the same skull as here, only we try to reconstruct it from 3 views rather than 64. Here, this is an indoor scene reconstructed from like quite a lot of images, but these images have to cover a larger part of the scene, so each part of, like small part, is only covered by a few cameras, and then it's hard to properly train the network. And here you see another room trained from like roughly 300 images. So the issue here is that the measurements that you have for each part of the space are relatively sparse. And the problem with neural radiance fields or these vol-SDF is that you're training a network that actually has a lot of capacity, meaning there are many ways to actually overfit to the scene. Here's an example where this neural network is trained from 3 views, and you can see that it's able to perfectly explain the individual views, but the interpolation doesn't make any the interpolated results don't make any sense. If you add regularization, you can get something much more meaningful, but still there are a lot of artifacts in these scenes. So the issue, as I said, is that the general problem of reconstructing volumetric representations from a few images is rather under-constrained. There are many configurations that explain the input images, but that do not lead to valid scene geometry. One way to get more constraints is to actually not just look at images, yeah?
So I just wanted to mention the previous
Yep.
paper that showed that regularizing nerves.
Yes.
What they regularize?
So so the best thing is to look at this. The idea, I think, if I remember the paper correctly, is to enforce some form of consistency from novel viewpoints, even though you don't have actual images there. You can still enforce some consistency on the feature representation learned by the NeRF. But I would need to look into the paper. I haven't looked at it in a year or so. Yeah, there's a lot of work on trying to regularize this training process in one way or the other. I decided not to go into detail here. If you're interested in this, I can try to figure out pointers to that. The one thing that you can actually try to do to get more observations is to not just look at individual images, but also get some idea about depths of the scene and surface normal. You might not always observe these, but nowadays there's actually good neural networks that can predict depths and normals from a single image, and they are meaningful enough that, for example, these are monocular predictions rather than using a depth map. These measurements are noisy, and depth is defined up to some arbitrary scale, but you get an idea of where potentially scene geometry could be and what the surfaces are. And that's what we used in a paper we published last year, where the idea is we do the standard training of a neural radiance field or a neural volumetric SDF representation, where we sample points along the rays, we evaluate them, we get like a distribution of density and color along the ray, and combine them into a single color based on volume rendering. But we're not only comparing against the image, but we're also comparing against like the predicted depths against the depths that we get from a neural network evaluated on a single image, as well as normals that we get from the single image prediction. And that to some degree helps to regularize the scene because you get more observation, you get more data, you get a better idea of where the surface should be. And here you see the difference between essentially taking the original Vol SDF formulation and only training on images versus adding these additional monocular cues to a degree where you actually get something meaningful from 3 views only. You get much cleaner geometry here and here as well. So here are some results showing what we reconstruct in the scene. And this is the same number of images versus what like a standard classical multi-view stereo pipeline would be, that is using no learning, versus what this Vol SDF method that I explained before gets, versus what another approach that trains in your volumetric representation, but also has tries to reason about orthogonal surfaces or planes. And this simple idea of getting monocular priors works quite well. Here's another example where we are able to reconstruct the scene quite well from relatively few images, and even compared to like a learned multi-view stereo approach, which is this one. We're doing quite well. And it turns out that depths and normals gives you best results, but even just having access to depths or normals itself is actually quite useful. So this is without any cues. This is what you get if you just have depths. This is what you get with depths and normals. And this is what the ground truth looks like. We are not using depth cameras here. We're using normal cameras, but we have a neural network that for each image independently predicts depths and predicts normal per pixel.
Oh, and that's good enough.
So it's what's a bit hidden here is, so this depth is defined up to some scaling factor, and if you take two images, the depths might not be consistent. So as part of the training process, we're actually learning like consistent scaling factors for two views. And then based on this, we are able to compare the depths predicted by the network in a way that is with the predicted depth values. And at the beginning, so we are not taking this as face value as saying this is the precise position of where the point should be, but we're starting during the first part of the training, we're saying all the depths, we have a higher weight to depth loss, and during training we decrease the importance of depth consistency more and more because we trust that the network is getting better and better at predicting depths, and at some point you don't want to force the network to fit too noisy predictions.
So the depth and formulations are
They are learned, yes. So we didn't train those networks ourselves, it's just that I think the paper was released in 2021. They started training those things on at a massive scale, and all of a sudden you actually started to have meaningful things. Before this, the single view depth predictors that I've seen they kind of looked good on few examples, but they didn't work well in general. This thing seems to work really, really nicely.
And so you train these networks alongside?
No, these are trained on massive training data, and we assume then it will generalize meaningfully in a reasonable way to the data that we are using. And we're going to look a bit into what's called NeRFstudio, which it's a very nice project that combines different NeRF implementations with nice tools and a very nice viewer. So this includes, for example, the instant NGP formulation, I think also the Plenoxels. We're going to look at a nasty example, which is like a very, very reflective surface from which we want to compute scene structure, which we want to model. And the workflow is this: you start with images or a video. If you capture a video, you extract images from it. You run the images through structure for motion, for example, call map or reality capture, to get camera intrinsics and extrinsics. You convert them into some format that's useful for the software package that you're using to estimate the NeRFs, and then you start training. So let's look at this. I'm using reality capture here, which is a commercial software just because it's much faster than CallMap, which would be the open source alternative. I'm starting with reality capture. I am going to find the right folder. Going to import images. So here I essentially told reality capture that all images should have the same intrinsics. I start the alignment process, which will extract features, match features, and then estimate camera positions.
Makes sense to maybe combine these two methods and make an equal position list, so maybe they can incorporate in them?
Yes, I think that makes sense. There is a paper, I don't have the precise reference yet, that is doing a point-based representation of the scene. So they train a network that takes point positions with features and then predicts the color and density for this. So if you start with a point cloud, you have some features attached to these points. You shoot rays for each point that you sample. Along the ray, you find the nearest points. You interpolate the features and use that for rendering. And then as part of the training process, they try to densify the point cloud in order to improve quality. So that would be one example in exactly that direction. You can see this is what reality capture estimated. This is the center of the pool. There's basically nothing there. It has some images, something reconstructed along these parts which have relatively matte, non-glossy surfaces. We're going to export the alignment, which is relatively efficient. Then we're going to process this in a way that nerfstudio can handle by essentially calling NSProcessData, telling it this is reality capture data, this is the directory where all my images are, this is the file that I just generated, which contains intrinsics and extrinsics, and I want all my output in this folder. This will take a bit because it's essentially reading in the images and the poses, and it's also creating downscaled versions of those images, which is actually the most time-consuming part of the process. Here it copied the original images. It's creating downscaled versions of these images at multiple scales. And that's the most time-consuming part. What it will also generate is a file called transforms.json, which essentially stores the data in a way that nerfstudio likes to read it. There's a camera model, which essentially says, I would like to use OpenCV's camera model. The image, this is the height and width of the image, the corresponding image name, focal length values, principal point, radial distortion parameters, and then this is the transformation matrix that either goes from world to camera or camera to world, I don't remember. And you essentially have this for each individual image. You are allowed to actually have different intrinsic calibrations for each image. And once you have processed the data, you can start the training process. I want to train a model that's called NeRFacto with the data in this folder that I generated, and I want to write all my output to some output directory. And it will start, it will load the data, and it will start training. It actually connects to some local port and creates a website which you can open where you can actually visualize the training process. So here you see a visualization of the trained radiance field that gets updated over time as training progresses. No, I think this is just a redirect. I don't think the training process is running on my machine. It's yes, I think they send I haven't looked at the code. My understanding is that they are not sending data to some other, to some external service, but that this is just a redirect. The website is there, but it redirects the data loading to your local thing, I think. It used to have a function to show the original images. It worked yesterday. So here you can see the Neural Radiance Field. You can see that it's able to capture view-dependent effects, such as this house becomes reflected in the surface. But also we are currently we have done 5% of the training. I have a version of this where I trained it actually for half an hour. So you can see that after training for half an hour, you get something that's much more detailed. It's still blocky because what's happening is that as you move the camera, it renders low resolution images in order to do the rendering fast enough. And then as you stop, it starts rendering higher-end, higher resolution images up to 1024 pixels on the side. And I'm not saying this is perfect, but it's actually, given that it's a quite nasty scene with something that doesn't have a properly defined geometry, it's doing quite well. You can also look at predicted depth values, and you can see that it's able to like model these thin structures that actually are not reflective, but it doesn't really have like a clearly peaked surface on this reflective and refractive part. Rather, it will distribute the density somewhere there, which is enough to give you like realistic renderings, but not enough to get geometry. So in that sense, you can compare it to the dense reconstruction that you get from reality capture, which looks like this. So here you can see that reality capture is able to, I think this is a textured model, is able to do reasonably well on this parts of the scene that are not reflective, but the reflective parts are actually missing. With the Neural Radiance Field, you get at least something that renders realistically looking images from this. But yeah, as I mentioned, you don't get geometry there anyway as well. So it's similar there. There's no clear geometry there. You can see that it's actually able to run, you're able to train different models. Depending on which model you use, you might have less parameters that need to be evaluated, or shallow network that will make rendering faster. The Plenoxel approach is making rendering faster because you don't need to evaluate a neural network at all. In terms of shallow neural networks, you could also just subdivide the scenes into small parts, and then for each part have a very shallow, like a few layer neural network that will be efficient to evaluate. There's a recent paper that combines traditional mesh rendering with a radiance field. So the idea is you first render a mesh, you render like features distributed on a mesh, and then feed the features into a neural network that gives you color, a view-dependent color. But the idea is that the network is actually able to account for the fact that your mesh is not perfect. So it's offering some sort of correction term close to the surface. So this is the type of things that you could do to make rendering faster. You can cache neural radiance values typically to some degree, because especially if you're rendering like a trajectory, you're getting close, 3 points close to each other that get evaluated. You can cache some outputs of the radiance fields there so that you don't need to run it completely from scratch.
And on the scale of the computational requirements, would you expect this to be able to run decent quality on, say, an iPhone, or do you need a GPU, or?
I would expect that at some point you can run this on an iPhone, given that all these companies are investing into chips that can do tensor operations very efficiently. So that would be my hope that with all these specialized hardware, you might be able to run this on mobile device at some point, yes. So for those who might not have heard about it, there's this thing called Dream Fusion, which is essentially takes a text prompt as input and then tries to create a 3D model. And I think this is a NeRFs 2022 paper or something like this, iClear. I think it was accepted at some point. So this is like part of the text input, and the corresponding 3D model is seen here. And the way that this works is, I've read the paper a while ago. What they don't have is training data that would link text and images, text and 3D models. This is typically something that's hard to get. So what is there is there's a lot of data that links text and images. For example, Stable Diffusion and all these other generative models are trained on text on this type of data. So they start with essentially something like Stable Diffusion, which gives them, for a given prompt, gives them an image. And then they try to translate this into 3D model. And the way that they do this essentially is that rather than learning a 3D model, they, like an explicit representation, they learn a translation into a radiance field that they can then render. And they have some regularization terms, such as if you look at all these models that they're showing, they are actually quite symmetric. So they actually have, I think, some prior that says, I would like to create models that are more like reasonably symmetric as a way to stabilize the training process. What else they do to make this train, I don't remember. I haven't read the paper in like half a year or so. But that's the gist of it. You try to train like an embedding from images to radiance field, like neural radiance field parameters, and then you can render these neural radiance fields. So I hope I convinced you that like implicit neural scene representations such as NeRFs are interesting in the sense of that they can handle a lot of complex effects, produce accurate 3D models, at least under certain conditions, and can potentially generate compact scene representations. They learn from images, and they're currently a very hot topic, but there's, I mean, the original NeRF paper came out, was published less than 2 years ago, or about 2 years ago. So they're still very much in the infancy. There's a lot of things that still need to be done, scalability, reducing training times, like we are far away from 3D reconstruction algorithms that can run on like classical algorithms that can run on real time on mobile devices. But we're getting, the nice thing is we're getting more and more software. I showed you NVIDIA's Instant NGP, I showed you nerfstudio. We actually have something called SDF Studio, which does the same thing as nerfstudio, just with signed distance function-based representations. One issue here is the whole thing is that there's actually a very large body of literature. Like a couple of years ago, GANs used to be a very, very popular topic with a couple of GAN papers published on arXiv each day. We are about at the same thing with NeRFs. So it's very hard to keep up with literature, but there are some good starting points. There's a blog post by Frank Dellert, I think 3 of them. There are a couple of survey papers that are reasonably good if you want to get into the topic. But yeah, the downside of looking into a very hot topic is that keeping up with literature is close to impossible. Okay, yeah, that brings me to the end of it. Thanks for listening. If you have any more questions, either ask them now or like bump into me later and ask them. Thank you.